Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So today I'm going to be picking up from where I left off last time, where I started talking about deterministic finite automata, or singular deterministic finite automaton. So I gave this the formal definition of a DFA. It's a five tuple, and today I'm going to be helping you further understand the concept of a DFA. We're going to do some examples and we'll design some machines today. So I'm pretty excited about that. So just as one remark from last lecture, I wanted to show you what happens when I could take a machine, I could change the starting state. Last time I made this S2, I'm going to switch it to S0 just for this purposes. So I just wanted to show you how the machine processes strings at that time. I'm going to do the same thing, but with this slight tweak on the machine. So M1, if you're doing this, note that the example I gave last time is perfectly correct. It's just that I want to proceed with S0 because I don't know. You'll see later why it makes a little bit more sense when you see what this thing might actually look like. It's a little bit more intuitive to play around with. Anyways, just as a reminder, I want to remind you of what the five tuple or quintuple represents. So remember S0, this set S0, S1, S2, this is the set of states, Q. 0 and 1 here. This is our set of input symbols, which is given by an alphabet, sigma. This is our transition function, delta, which usually is the thing that takes a little while to describe, which I'm going to give you nice, easy ways of describing delta today. This is the starting state. So often it's denoted as Q0. Often when I design the machines, I'll usually use Q0 as a state in the machine, but it doesn't have to be. Like here, I have S0. So S0 is just the name of a state. And these are my final states, F. Final or accepting, just to be more precise. Okay, so last day I gave you this transition function. So everything about the example is the exact same except the starting state. I want to process another couple strings with this just so we can get a feel for this. And once I do that, I'm going to transition over, pun intended, to describing to you some simpler ways of talking about this transition function. That for you, it will look like something that you can actually pick up and put on a computer. So anyways, I thought I would start off with an example with a string 10101. So remember, you got to imagine it like the machine reads the tape one way in. It's a read-only tape. It kind of pulls it in, or the machine kind of gobbles up each symbol one at a time. So I start off in state S0. That's because that's the starting state. I read the 1. Because I'm in state S0, I refer to the transition function. I have S0. I read, what do I read? I read 1, right? So delta of S0 and 1, it tells me I should be going into state S0. So I'm still in S0. Then I read the next symbol. I read 0. I compute just the delta for S0 on 0, which is just S1. And so on. I could do that for each one of the symbols. I'll jump to S2, then I'll go to S1, and then I'll go back to S2. And then the great thing is when I'm done reading my input string, so when I'm finished reading this whole thing, I can tell you whether the machine is in an accepting state or the machine must reject the string W. So S2 is a final state, hence it is going to get accepted by the machine. Okay, so this example makes sense for everybody. So I'm just reading each symbol one after the other, and I put it into the transition function. Like I said last time, you're going to think of it like a lookup table, which is a natural way of representing this transition function. I'll get to that in a moment. So I want to do one quick other one, just because I gave you one that is in fact accepting. So imagine I give you, I think I have... let's go 0010. Okay, let's go there. So just to make sure we're clear with everything, I'm not going to write any steps here. We're going to walk through it together. So I start off in what state? I start in S0, right? I start in S0. I read the 0. S0, and I read the 0. I go to S1, so my current state is S1, right? And now what I do, I read 0 again. I read 0 again for S0. But now I'm in S1, right? So it tells me to go to S0. So my current state is S0 again. Then what do I do? What do I do? I read a 1. Could somebody in the chat tell me what state I should be going to? Is it S0? Yeah, S0, right? Because if I'm in S0 and I read a 1, it tells me to go to S0. So I'm still in S0. Okay, now we got one more symbol left. So tell me where does this, where are we going to transition to from reading a 0 now? S1, perfect. So our current state is S1. What does that mean? What do we do with this string W I have right here? Is it accepted or rejected? Rejected. So this gets rejected. It gets rejected by the machine. So there's going to be some strings that get accepted by this machine, some that are going to get rejected by this machine. We're going to be curious about the ones that get accepted by the machine. Those are going to form the language of that the machine recognizes. Okay, so is this idea clear with everybody, that we just read each symbol one after the other? We just read the transition function, and then when we're done reading the string, we determine whether it's accepting or rejecting based on if it's a final state. I think we're good? Give me a thumbs up. Don't be shy. Okay, good. Okay, very good. If we're doing that, that means we're doing really good. Okay, so now I want to talk about how we can represent DFAs, because you might look at this transition function I had over here and be like, Dan, do I really have to write out this function and like write all those tuples every single time? I'll make you do it once on the assignment, and then other than that, I'll probably just want you to try using one of these approaches instead, pretty much for the rest of the term. Because I want you to make sure you at least do it once. Okay, so writing out a DFA can be quite cumbersome if you really just are like, hey, look, I just want to give a quick description to somebody about what my DFA looks like. My automaton looks like here. So sometimes it's even unintuitive. I'm going to give you one representation that for computer science students or computer scientists in general would be very natural. You'll be like, hey, look, I know what that looks like. I could tell you exactly what it does. So even if you didn't even have a technical background with this, you'd have a pretty good idea of what it does. So I'm going to give you a couple ways that you can understand a DFA, in particular delta, the transition function. So the first one is, of course, the transition table. This one I don't have as much fun things to say about it. So what do you think? Think of a lookup table. So think of a lookup table. So for example, let me just go back over here, and I'm going to draw out a transition table for our example over here. And I almost guarantee you, okay, is there anybody that's never heard of what a lookup table is? So a lookup table is very simply, it has rows, it has columns. I put in input, it tells me what I should provide back as output. You may know this in other forms. So for example, as in a data structures context, you may know this as a map or a dictionary, for example. But in our context, we're going to have multiple columns, just as opposed to just input in, output out. So let me just draw out one of these, and you'll see quite quickly how nice and easy it is to describe one like this. Okay, so I'm going to, for each one of my states, I'm going to have a row. So notice these are all three of my states. And I have two input symbols. I have 0 and 1. And because I want to make sure I have all the information I'm going to need, I'm going to indicate the starting using an arrow. on the state that's the starting state. So for example, if S2 was the starting state, I would draw an arrow right here. For final states, I'll indicate these with an asterisk like this. So remember, S2 and S0 are final states. And now, here's the great part. Everything I've just described here, I only care about these entries, all right? I'm just going to fill those into the table. So I'm just going to read them off. So I got S1, S0, S1. I got S0, S2, and S1, right? So this is what the transition table would look like. And the way you would interpret it is when I read a symbol in, I look at the row of my current state. So for example, if I'm in state S0, I read this row, and if I'm reading a 0 in, I read the intersection where the column meets the row. So this would be the current state. This is the current symbol I'm reading. So if I read S0 and I read a 0, I get S1. And is this intuitive for everybody? All I'm doing is I'm just drawing out a table that's just representing the same information from the transition function. Nice and intuitive, right? Yeah, so you notice that that's much easier to describe. I don't have to write delta all over the place, right? Okay, so I'm going to now, so are we all good with the transition table? So just keep in mind those couple of conventions. I know that CISPR does not use the arrows and stars. I know Hopcroft does, but I find including that information, you tend to get a lot more information about what the DFA should be like. This would of course be information if you were to actually implement this, you'd keep the table. Those other bits of information with something you would encode elsewhere, right? Okay, so the second one, this is the one I really like. And hopefully you'll get some appreciation for it too quite quickly, is a so-called transition or state diagram. So earlier on in the course, I told you that I was going to very often want to think about machines like state machines. And oftentimes, do you remember my example where I had the toggling switch? When you looked at that, it was really intuitive the way I described it to you. I read, okay, if I toggle, I go from the off state to the on state. If I toggle again, I go to the on state to the off state. I want to have some natural way of doing that with DFAs. And this is a nice way of describing delta. And in fact, you could get the entire description of the DFA from just the transition diagram like this. So I'm going to use a labeled directed graph with loops. So might know those as self loops. So we can construct a transition diagram as follows. So I'm going to describe the process to you, and then we'll use it on the example over here. As follows. Okay. So first, we're going to need vertices for each state. So that means that for each Q in my set of states, there is a vertex or node labeled Q. Let me just switch my marker here. So in my diagram, I'm going to have nodes or vertices, whatever you'd like to call them. And each one's going to be labeled by the state's name. So for example, in my first, for instance, with my example over here, you'll remember that I have states called S0, S1, and S2. Those would be what I would label these vertices or nodes. So let me just get the next part. So this is the part that we need to be careful with. So we're going to have directed edges, or arcs, if you're familiar with that terminology. for transitions. For transitions. For input symbol X in a set of symbols, input symbols, and states. I'm going to possibly keep that singular or not. P and Q in my state of, well, my set of states. If there's a transition from P given symbol X and it equals Q, then you're going to include arc PQ labeled X. So if there's a transition from one state to the other, you're going to draw a directed edge or arc in the picture, and you're going to label it the symbol used to transition from that one state to the next state. Just as one remark about this, for simplicity, if there are multiple X in the set of input symbols with the transition from delta Px equals Q, then one can label arc PQ with the list of all such input symbols. So all I'm saying is, if there's a transition from one state to the other, and there exists another one using another symbol that goes from the same state to that other state, then you just label the arc or directed edge with, you can label it with the multiple symbols. So for example, if, say, I transition from one state to the next state using both either 0 or 1, I can label the arc 0, 1. But like I said, it's a matter of convenience. If you were to implement this on an actual computer, you can either store a list of all the symbols, or you can have just 2 arcs. This is just to make it a little easier to draw the diagrams. Is that clear for everybody? That's usually the part that's a little bit tricky. You'll see, once you see the picture, everything should click if it doesn't yet. Okay, so that is part B. I'm going to finish it up over here. So let me just move on over here. So while that's happening, are there any questions so far? Keep in mind that I'm going to be indicating the start state and the final states. That's the only parts that are really left. I've already almost the entire idea of what the transition diagram should look like. Okay, so it's okay if I erase this example right here? I'm just going to put the description. Okay, I see some thumbs up. Awesome. Awesome. You guys are awesome. Let's do this. Okay, so we have to indicate the start state. So we need to indicate the start state. All you do is you include an arrow. Include an arrow toward the vertex that is the start state. The start state. If it's called Q0, then you go to Q0. And note it's not from any other vertex. So this will just be some dangling edge that just it's pointing out from the ether, okay? It's not one that's pointed, it's coming from any other vertex or anything. It's just going to be an arrow. You point it at the start. You may even indicate it literally by adding start on top of the arrow. That's what I usually do to make it a little easier to read. And this is this is what I consider my favorite one, is you have to indicate the final states. So all you're going to do is you're going to double circle. You'll see what I mean by double circle in a moment. Double circle all final states. All those in F. It's worth noting that all the other states, they're just going to be circles, just a single circle. So let me do the exam. So first, hopefully my writing there is all right. It looks like it kind of melted like an ice cream cake outside in the summer. My apologies. So let me draw the transition diagram. I'm just going to get rid of this rejected part here, even though that looks pretty fun, but no. So let's draw the picture. Okay, so I'm going to need three vertices or nodes. So I'm going to have 1, 2, 3 like this. I'm going to call this one S0. I'll call it S1 and S2. Those are what I was supposed to label them, right? And now what do I need to do? Well, let's do step B. So step B was I need to give all the arcs to the transition diagram. I almost tripped over that. That was pretty epic. So anyways, let's get started. Okay, so let's see here. So the easiest way you could check is if there exists a transition from one state to another, you're going to draw an arc. So all you're going to do is you just read these off, or if you already have an idea what they should be, then you would just straight up just draw the arc. So let me see. So for S0, and I read in a 0, it tells me to go to S1, right? So I'm just going to draw an arc, and I'm going to label it the symbol that takes me there. So I would read a 0, right? Am I clear, everybody? So all I'm doing is I'm just going to draw an arc from one state to the other if it could transition on that symbol. Okay, so how about 1? What should I do with 1? Well, 1 here is S0, right? So I can either draw a loop. So I draw a loop. I label it with a 1. That's the symbol I use to transition from S0 back to S0. It didn't really go anywhere. Okay, let's look at S1. By the way, this is everything I could transition on for S0, right? Okay, S1. So I need to draw an arrow from S1. Where do I need to go? I need to go to S0, right? I need to go S0 on 0, right? And how about 1? Where does 1 need to go? So I have an arc that has to have 1 on it. Where does it go? It goes to S2, right? So I'll draw an arc like this. I'll put a 1 on it. You'll see why I kind of crooked it like that. It's kind of fun. Okay, how about S2? S2? Can somebody tell me what should I draw from S2 here? Any ideas? So I got to go to S1. And the great thing that you'll notice is that both of them transition regardless of 0 or 1. So I'm just going to list that as 0, 1 like this. Like I said, yeah, perfect. So now that's part B. Part C, all I have to do is indicate the start state. So I just draw an arrow over here. I say, I'm going to write start. I find I tend to do that because it's a little easier to read. But it doesn't hurt, like, if you just left an arrow like that. If you drew an arrow without saying start, some people do it that way too, but I won't worry too much about that. Lastly, this is my favorite part. I got to indicate the final states. It's S0 and S2. S0, S2. So I doubly circle them. So notice now I just drew an extra circle. So now notice that if you read this, isn't this a much easier thing to follow from that over there? So here's the intuition of how you could read the transition diagram, and this is why I really like it. Okay, so if I give you a string, the dolly just started going that way. Anyways, so if I read a string, so for example, if I was reading, say, let's go 1100 or something. All I do is I say, okay, I put my finger in S0, I read the 1, it tells me, okay, I back at S0, I read another 1, I back at S0, I read a 0, I go to S1, right? And then I read another 0. I go back to S2. It's a final state, so I would accept, right? So do you see how nice, like, this is so much easier to play around with than having to compute the delta every single time. Does everybody like that? Is that kind of neat? So you don't have to look that up and look up delta every single time. Sometimes this formalization of delta, we're going to see an example next time where we're actually going to formalize this notion of delta so that we could determine any state the machine is in at any given time, which is quite interesting in its own right. Hence why it's deterministic. So are we okay with these two representations of a DFA? So transition table and transition diagram or state diagram? Are we all good? Give me a thumbs up. I just want to make sure everybody's on the same page. Because if so, we're going to start designing some machines. Yes? Okay. So the start is just an arrow. So I just point, I just draw. Okay, no, you don't. So remember, the biggest thing you want to be aware of is that the start state is always the fourth parameter of the DFA. So that's what you describe what the start state is. So it could be called, like I could call any of these states anything I like. They're just symbols. So it could be called Q0, Q1, Q2, and that could be Q0 right there. It could be a bunch of strings, you know, like call them like on and off. That all represent one symbol. They could be anything really. It's just as long as they're symbols that I could represent that encode that state. So the fact that it's S0 here, it could be called cat, as far as I'm aware. It could be a cute little symbol that represents a cat. As long as it's just some label that represents a state that I have encoded as a part of the DFA. That's all it is. So there's nothing special about the name S0. Is that answer? Okay, so yes, they're final states. So S0 is a final state, so I've double circled it. S2 is double circled because it's a final state. S1 is only singly circled. So it is not a final state. No, thank you for asking. No, I really appreciate it. It's these little things, right? Like these little things do creep in. So I appreciate these kind of questions. It's very important. Excellent. Are we all good with this? Because we're going to start designing some machines. Perfect. Let's start having some fun with this. So like when you're working on the assignment, I may ask you like, okay, give me a DFA, define it formally for me. Like I may ask you to write out the entire transition function. I may, for example, tell you, oh, give me the transition table. Oh, give me the transition diagram. Like these are all the same way of representing different things. Each one sort of has its pros and cons. For example, the transition table, like if you're more of a hardware person, you might really like the idea of the transition table because it's something you could conceivably put in something that's like a digital circuit, right? Like you could imagine this as a bunch of states. I have a lookup table. I could transition between them. For somebody else, this transition diagram is very intuitive because it's also a graph. So anything you could do with a graph, you could do with one of these transition diagrams. In fact, it's quite nice if you think about it like that. You might ask questions about the transition diagram. For example, is there a state that's reachable? So you might use some of your graph theoretic algorithms you might be familiar with or may not be. For example, like say your typical graph traversal algorithm, like a depth first search or a breadth first search. You can do all that kind of stuff on these kind of diagrams. anything you learned about graphs at any time in your past, or if you've never heard of what a graph is, that's okay too. I just want to put that out there because I like to make sure you see a lot of different ideas. Okay, so let us proceed. I'm going to start off with something kind of cute. So let's start off with, so I'm going to try to make a machine. I want to try making a machine that accepts binary strings. Binary strings with an odd number of zeros. So that's what I'm going to first try to design with you. You're going to see that I'm going to present you some little tricks for designing these machines. So the first thing I got to do is I want to give you an idea. So I want to build a machine that if I give you a binary string, it's just zeros and ones, I want it to be able to tell me it accepts if there's an odd number of zeros in it. So I'm going to present you, first I'll present you an idea. So actually, do you want to see the machine? Let's try drawing out the machine. Let's just get our hands dirty and I'll try justifying the idea. Yes. Okay. Okay, so if, for example, I said that I wanted an even number of zeros, for example. Yeah, if I wanted an even number of zeros, that would mean that it also includes no zeros. Yes. Yes, because it just zero zeros is by definition even, because it's twice the multiplication of some integer. Zero's an integer, so yeah. Perfect. Yeah, no worries. No worries. So let me define, let me try defining a DFA for you. I'm gonna let I mostly want to apply the ideas we've seen here. I'm gonna define it, I'm gonna call it M odd like this. Q, sigma, delta, Q0, and F. I'll define it in this way, where I'm going to have Q0. I'm going to use only two states to do this. You're going to see this and be like, that's pretty cool. Cool. I'm going to have sigma. Remember, this is going to take a binary string, so I'm going to have input symbols being 0 and 1. What's the start state? It's S. It's Q0. It's Q0. And of course, the final state will be defined as follows. So I'm going to define it as Q1. Oh yeah, and I also have to actually tell you what the transition diagram looks like. So I'll encourage you, I have it in the notes. You can take a look at it later. I have also the transition table in my notes, but I'm just going to do the diagram because it seems like a lot of people are gravitating towards the diagram, and I want to show you the diagram anyways. Where delta is described by the following transition diagram. By the following transition diagram. So here I'm going to draw a picture. Let's draw the picture. Here, I'll walk you through the rationale behind this. So let me see. So I'm going to draw two states like this. I'm going to make, I already told you Q0 is the start state. So I'm just going to draw an arrow here. I'll indicate the start. Because this is going to be Q0. This is Q1. And I'm going to define it in the following way. So I'm going to draw a self loop on Q0. I'll label that with a 1. I'm going to go from Q0 to Q1 with a 0. And from Q1 to Q0 with a 0. And I'm going to have a self loop again on Q1. This time with a 1, just like on Q0. Does everybody see the transition diagram? But one thing I haven't done yet is indicated the final state. I want to just explain the idea behind what I have here, and I'll tell you what will probably be a good idea for the final state. So I want to try it with just some strings, just so we could see what we could do with this. So imagine I give you a string that is, say, 0, 0, like this. You'd agree with me that 0, 0 does not have an odd number of zeros. It should get rejected, right? So I start off Q0, I read a 0, I go to Q1. And then I read another 0, I go to Q0. So it's not a final state, so it would reject, right? Keep in mind, I haven't told you what the final state... Actually, I did. It's right there. But I'm not going to draw it just yet. I want to motivate it for you. So, okay. So what if I have 3 zeros? You would agree with me that it'll bounce back over to Q1, right? But here's the neat thing. Now imagine if I were to put a 1 here, or a 1, or as many 1s as I like. Notice that if I read a 1, it will keep me in the exact same state I was in before. So I don't bounce around. So the whole idea here is if I can get it so that I can make it so that I could go between these two states, but ensure it happens an odd number of times, and if I make Q1 the final state, you'll notice that if it's an odd number of zeros, I'll end up over in Q1 as opposed to Q0. Does everybody see that? Is that kind of slick? So this actually this brings me back to the question really of what was brought up before about even numbers. I want you to think about this for one moment. Okay, what if I wanted to make it so it accepts on an even number of zeros? Yeah, it would be Q0, right? Do you see exactly how the design idea really boils down to me using the fact that this is like a pathway between these two? And all I'm doing is I'm alternating on them. And they change. You can think of it like this one represents the even zeros. This is the odd zeros. So if I bounce back and forth between these two, I could easily figure this out. And I could, if I wanted even an even number of zeros, I could switch the final state to this one. In fact, on the assignment, I'm going to ask you to prove that this happens with every single DFA. If I give you a language that I want the DFA to work with and recognize, if I flip the final states, you actually get the complement of that language. It's pretty slick, right? So this is a pretty neat example, right? So obviously, just because, for the sake of notes, I'll write down a design idea. So design ideas, that way we have the justification written down. Observe that we can have as many ones as we like. But the number of zeros required to reach Q1 is exactly equal to 2k plus 1 for some non-negative k. And which is, by the way, the definition of a positive odd number, right? So this is neat. So you'll notice that by drawing the transition diagram, I basically give you all the information you need to know about the DFA. But just for the sake of completeness, I wrote the entire thing out anyways. So if I want to ask you what's the formal definition of your DFA, I'd ask for this information. And if you want to describe delta with a transition table, you could do that. You could also describe it as a transition diagram, or you could literally describe delta in its entirety to me. Seems like a lot of options, right? In fact, as I said, I could get pretty much all the information I need from the transition diagram. So that's what I'm going to do for the next examples here. So let me do another example. So let me just zip us back over that way. I'm going to switch markers too, because this one's starting to not be the most trustworthy marker. Hence the melting like a microwave. Okay. Okay. Actually, I have a question for you. Just this is as a remark. I have a question. This is just a question for you. Okay, question. Can a DFA accept the empty string? So think about that for one moment. So I see, so answer me in the chat or feel free to blurt her out. Can a DFA accept the empty string? So remember, a string that has no symbols is the empty string, right? But remember, I want you to, yes, it would be in the start state, exactly. So how can I make a DFA accept the empty string then? Ah, correct, very good, very good. So the answer is, of course, yes, perfect. So if the start state is a final state. Perfect. That's right on the mark. Perfect. I like this. So that being said, you got to also keep in mind that case, because sometimes that would creep into some things that you're up to. So for example, with my previous one, if I wanted to make sure that my strings were at least, like they had at least one symbol, and I wanted to have an even number of zeros, I couldn't, for example, do what I did over there, because I would need to make sure that it does not accept the empty string, right? So I'll let you think about that. Let me switch gears, and I'm going to do an example where I'm going to show you how you can make a DFA accept a substring. So I want to just first give you a little bit of notation here. So for some DFA M, we denote L of M to be the language of a DFA. So to be clear, this is another way you could phrase this is the language recognized. The language recognized by M, which of course is just all the strings that get accepted by M. So if you're wondering what L of M is, I'll very often use that notation to describe the language that the machine accepts. So let me do another example here. So I want to make it so, actually, just before I get there, actually, let's get rid of this example part, because I want to go back to that one example. So if I were to write out that for L of M odd, just as an example, so this is indeed an example. So L of M odd, this would be the set of all binary strings such that W has an odd number of zeros. So if you're not familiar with the set builder notation, this bar means such that. Some people use a colon. That's okay too. So this is one way I could describe the language of the previous DFA. So naturally, people could throw languages at you and ask you, can you design a machine that accepts on that language? Always. It recognizes it. So now here comes the example. And the great thing is, I'm going to try to, so I'm going to build a DFA that recognizes so I'm going to I'll write it down this way. So W such that W has the form x0, 1, y for some strings x and y, consisting, it says consisting of zeros and ones. So I'm going to design a DFA that does this. So if it's okay with everybody, does everybody have to go anywhere immediately after this? I want to see if I could get 2 examples in, and I only will need a few more minutes after this. Just need a few minutes. Okay, because I want to make sure I could give you one more example, and I could kind of give you one fun definition at the end. Perfect. Okay, so I want to design a DFA. Now, if you look at this, remember, x and y, these are going to be these are binary strings, right? So I want to make sure that my binary strings always have a 0 and a 1 as what is called a substring. So 0 and 1 better appear in the binary string. Those are the ones that are going to get accepted. So in the past, you may have seen things like, hey, look, if I want to find a substring in a string, you may do this in a programming language. I'm going to show you how you can design a DFA that actually does this for you. So let me draw a fun picture. Okay, let me just, here we go. So let me draw a picture. So I'm going to give you a little tip with these. Okay, if you want to have it so it has a substring that it accepts on, the idea is that you may want to include the substring as a path on the transition diagram. That's the first tip I can usually give with this. That's usually the first go-to thing you would try to do with this. So I'd make a start state. And I'm going to need, let's make 3 states. Because I want to make sure it accepts on, make sure it has that substring 0, 1, right? So I'm going to make sure I have some arcs here with 0 and 1 like this. So I know for certain, if I make Q2, for example, the final state, I know, assuming everything goes fine, to get to Q2, I have to read a 0 and then a 1. So the idea now is just to fill in everything else. But you have to be careful, because if say, the substring is something a little bit more complex, you have to be a little careful. But generally, you want to try to design a pathway like this. That's usually a good trick. So, of course, if I read a 0, I want to make sure that anything else stays in Q0. So a 1. So if I read a 1, stay in Q0. If I'm in Q1, now this is where a little bit of the intuition comes in. Okay. If I want to read this, I want to make sure there's a substring with 0 and 1 in it. If I make sure that if I read a 0, I stay in Q1, but if I transition to Q2, what can I guarantee? I could guarantee that if I stayed in Q1, the previous symbol I just read was a 0. So if I put a 0 here, that's fine. And anything else, I don't really care what comes after it. It could be a 0 or a 1. Does everybody understand the intuition behind this? So the trick I usually suggest is put the substring here, and then see if you could design the automaton so that you can take advantage of any of the transitions. Basically, this middle part is the tricky part. So if you're doing something more complicated, that's usually where the tricky stuff happens. So this is just an example of a transition diagram for such a language for our machine to recognize it. So isn't that nice? So all you have to do is just do this little trick here. Okay, so I'm going to do one more example. One more example. I just want to show you, because this one is a substring. You might naturally ask, okay, how can I make it so I have a machine that accepts on, so if I want to have, for example, at least 3 1s appear in every one of the strings I'm going to accept. How do I do that? What I'm going to do is I'm going to augment the idea I just described to you. So I'm just going to take the idea and I'm just going to extend it just a little bit more. But you'd see that a substring is a little bit more careful with the way you have to go about it. So let's do another example. So I'll quickly write this down. One's in a binary string. So I'll write this out a little bit fancier in the notes. So I want to make sure I design a DFA that accepts on at least 3 ones in a binary string. So we're going to take this idea of a path, just like I did before. And instead, what I can do is I'm going to have a chain just like I did before. I want to make sure I read at least 3 ones. But I have a question for you. How do I arrange them? So if I make Q0 the start state, can somebody tell me what I need to do with this? If I want to make it so that it accepts on any binary string with at least 3 ones in it, what should I do with the transitions? That's a very good suggestion. That's exactly what I would imagine you'd try doing here. Yeah, you'd put a chain. So notice that to get between the states, I require me reading a 1. Then anything else, you kind of keep it as junk to keep around in that state. So I have 0, and then I have another 0. And the last one, I could just take whatever. Perfect, perfect. See, like, isn't that wonderful? So this is one way you could approach this. So oftentimes these states, when you go from one state to the other, they sort of carry along any of the garbage so that you could keep proceeding to the next one and keep our count. So that's the idea here when we're trying to make sure we have at least a certain number of symbols in a string. So just one last thing I just want to end off with, and I'll let you guys go, is I want to define what a regular language is for you, because I've told you, like, oh, we're going to talk about this thing called a regular language. I haven't defined one for you before. I'll give you more intuition of what regular means in a future lecture. But all a regular language is a language L. A language L is regular. A language L is regular if some DFA recognizes it. That's all what a regular language is. Boom. Is that wonderful? Are there any last questions before I let you go for the day? I will stick around after if you have any other questions. So, okay. So if that's the case, we'll wrap things up here, and I'll say thank you very much and have yourself a beautiful day. And have a good weekend. I'll see you later.